In this video, we're going to look at the idea of the convolution, which is something most students have not seen before this course in any meaningful way, and which I think is underrated or over-mathematized when it's usually presented. So I'm going to make an attempt here, and let me know if it's successful or not, to explain what a convolution is and why you would ever do one. Because this is a big selling feature of Fourier transforms and also something we're going to see in Laplace transforms as well later in the course. So, convolution. The first thing is that it's a merging of two functions. So we'd have function 1 and we'd have function 2, and this little star symbol here represents the idea of convolving is the active verb between two functions, but the convolution symbol. And the key thing is that we get another function back. So we get a new function back. All right. First thing, just to note, which makes our lives a little bit easier, is that it is symmetric, at least in real values. If you have two functions and you convolve f with g or convolve g with f, it's the same thing. You're merging them and they sort of play equal roles in the mathematics, though sometimes it helps to reason or think about these, if you want, as one of them being the signal and the other function being I'm going to call it a spreader for the examples we see here, but it also has other roles we'll see in Laplace transforms a little later on. This terminology is more similar to what we've seen so far in the course. So imagine we're convolving a signal with some kind of spreader function. This is the definition of the convolution. And what you see is something that might not be, I don't think it's obvious at all as to what it means. But let's just walk through some of the pieces of it before we get into an illustrative example. The key thing is that there's this new variable tau, and it's called a dummy variable. And the reason it's called a dummy variable is because when the integral is over, after the integration, when we integrate from minus infinity to infinity for tau, well, the tau gets subbed in. We sub in the positive infinity, we sub in the negative infinity, and so the tau disappears. And so it doesn't play a real role in the final value. What we end up with is just a single variable left, which is t. The t depends on, the t is one of the inputs here, but we're going to get our y of t back. So depending on what t value we pick, we can plug it into here, do the integral, and get the y value. Take our signal, somehow merge it with g, and get a new signal back. Let's go into an example that hopefully helps to understand why we would be using this thing at all. So, might be a little on the nose right now, but it's relevant to the examples that you're working with day to day. If we look at the COVID rate, this is in Canada, and this is of new cases that were reported on a given day. So these are days into 2020. Here's January, here's March and all its excitement, and we're around here right now. If we look at this graph of blue dots, let's call that here down here, this is our f of t, and it's our signal. You'll often see this graph here overlaid with what looks like a smoothed curve. And if you look at the details in most of those, you'll see something like a 7-day average or a 5-day average or a rolling average, some kind of terminology like that. And the idea is that when we have spikes and ups and downs in this function, they're real, but they're not the interesting part, or we can't learn too much about the overall shape of the curve, which is what we care about from individual data points like that. For instance, if we looked at this data point up here and said, oh my goodness, that represents the real rate going forward or backwards, that's the rate that we're going to have to deal with, we would be in big trouble. But fortunately, it's an outlier, and so it's much more representative to follow something like the red curve and go, okay, here's basically the rate we're talking about, with this one outlier being something we shouldn't factor in too heavily. So where does the math come in? Where do we get these kinds of formulas, like t's minus tau's, that kind of thing, in this rolling average? Well, let's just imagine one of these red points. So let's take this red point here. That has a value of, let's say, y of t. I'm going to say, let's call it y of 130. Now the naive way to calculate this would just be to take 1/7, we're doing a weekly average, and we would add up the f of t's, but not just the f of t's. In fact, let's make this general just to make it jump into the formulas. F of t plus some value, and those values would go, say, from the left and up to the right by 3. So if I go back 3 and forward 3 and include the value in the middle, that's 3 plus 3 plus 1 is 7. To get the average, add them up and divide by 7. Okay, that's a fairly straightforward mechanism. That's probably what the illustrators in a lot of these graphs do. But there's another way to think about it, which is going to seem less obvious, but it turns out to be more general. And that's to take a sum, and here I'm going to slide in my tau. Okay, so I'm going to add from tau equals 0 up to n. Well, what's the point of that? Well, what we're going to do is we're going to take every single value in our signal. So let's go down here to see it. We're going to walk across all our signal values. Tau is going to be 0, 1, 2, 3, so that you can think of it as moving through these tau values. And then to get the value at some fixed location t, so we're going to say, hey, at 130 here, what's the value I'm going to get there? Well, I don't just add up all the f values, because most of these shouldn't matter. What we do is we slide another function in here. We're going to call it our g. And yeah, I'm going to slide in the notation here, t minus tau. And we're going to see how that plays out. What does this g function look like? Well, this g function looks like this thing right here, which if I move this up just a hair, you can actually see the dots. There we go. There are 7 dots here, and they're all at height 1/7. And then there's a bunch of dots at height 0. And so g of t is just equal to 1/7, and then it's equal to 0. And this is for, I'm going to call it t here, t between 3 and minus 3. Oh, squeeze it in there. All right. And this is 0 for any other value. Now this does get confusing with the t's and the tau's and everything else, but let me walk you through the scenario. So if we're at 130, we're interested in knowing what's the red value here at 130. Well, I can take the 0th value of my signal, I plug it in here, and then I ask, what's g of, well, t minus tau, let's just sub in a number here for a sec. 130 is the one I want, but I'm looking at 0. So that's a difference of 130. That puts us squarely into the 0 range. So I get the 0 signal, the first signal value, times 0, so it doesn't count. I get the second value. If I plug it into here, I'm going to get 130 minus 1. Well, that still gets me a 0 multiplier. And if I keep going, the first time I'm going to get something interesting is when I take the 127th tau value. 127 for the tau value. Then I'm going to take f of 127. Okay, think about what I'm trying to do. I'm trying to get the 130th value here, which is the average of 127 to 133. Yeah, 127 to 133. That'll be a 7-day window. And then 130 minus 127. This is like a shift and linear tangent lines, all the stuff from first year calculus, all coming back. It basically centers this around 130. So when I get up to 127, I'm like, oh, I'm within 3 of that. I'm going to get my 1/7. I'm going to get this value here. And so I'm going to get 1/7 times the signal at this point here. And then you can see as I go to 128, 129, 130, 131, for the next 7 values, I'm going to get the 1/7 out of this g function times my signal. So what it's going to do is take the signal from 127 up to 133 and multiply each one of those things by 1/7, which is exactly the same as an average over 7 days in the kinds of calculations we did for the rolling average above. Now, what's the advantage of that? Well, first off, this starts to look like the math we saw in the convolution. So this is exactly the integral we have on the previous page of this form here. Only instead of an integral, of course, we have a sum. But if we take the limit, blah, 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 let the intervals go to smaller and smaller values, this would turn into an integral quite nicely. And the idea is that we could put any averaging function in here and still say that the rolling average, my y of t here, is equal to the convolution of the signal, f of t, signal, convolved with, or convolutioned with, g of t, which is our averager function here. So I take this function and I basically just, another way people talk about it is I move it along the signal. So I take this average function, I stick it at the front, and I multiply this point by this function here. Then I move it over one, then I add that to the total. And I keep adding up these combinations and eventually I get a new signal back, which is this red set of dots here. All right, we're gonna let that simmer, and then we're gonna take a look at an alternative formulation here. Same feel, with a slightly different goal in mind though, so hopefully it'll help tease out some of the common elements and the whys we do this. So here what we have is a grade distribution, and it's typically represented as a histogram, but it could also be represented as dots, where at the 80%, typically Queen's asks instructors to round to the nearest decimal point, or sorry, nearest full percentage mark. So at 80%, certain number of students got 80%, certain number of students got 81, and there's nothing in between. If we represent that as our signal, the kinds of questions people might ask if we look at this is, well, you know, where's the bulk of this, where's the bulk of the student mark distribution? I mean, you can tell sort of that it's mostly up here, but there's stuff down here. This isn't great. The histogram isn't great. It's way too noisy. It would be nice if we smooth it somehow, but in that smoothing, acknowledge that when we say a student gets an 80%, well, that's what we have as our best estimate, but realistically, they probably could have gotten anywhere between a 75 and an 85, just somewhere in there. Each individual student would have a real understanding bracketed around the mark they got as our ideal goal. Well, enter ye normal distribution here. What if we imagined around the 0 mark, say imagine 80%, if we see someone with an 80%, well, plus or minus around that, it's pretty likely they earned an 80, but maybe they also could have earned an 81 or a 79 just as well, and a 72 or 82 or 78 and so on. And we are comfortable with this kind of distribution representing the possible ranges of their actual understandings. This is a very metaphoric way to look at grades. But the idea is, if we did this, this would be acknowledging that these grades should actually have some wiggle room to them. Well, what we can do then is take each of these peaks, let's take the signal as dots here, and try to imagine, you know, how representative, or how many people really in this range got a 60. Let's make it even more exotic. Let's make it like 62. So pick some number here, 62%. You know, how many really got that if we acknowledge this possible range of values and probabilistic range of values? It's not a straight average. Well, what we do is we take the values a little lower than here, say this spike here, and we'd put this Gaussian distribution on here, this little normal curve here, and we'd say, well, these spikes can contribute this much to that point at 62. And then the next one would have its own normal distribution. But then this other one down here, we wouldn't scale it as much. It's still a normal distribution, but it's smaller because the signal is smaller there. And so if we added up all those normal distributions as we go, you'd start to get this red line here, which is our y of t, compared to our signal, which is, actually these are x's. Let's call these x's here. X's for our grades. And this is our g of x. So we have this merging function, which is on the same scale, but usually centered around 0 for these kinds of things, just like the averaging function was centered around 0 and was fairly narrow. It's the same idea here. If we wanted to get our y function here, well, we would get it by taking each of the f's. So we take all the f values. Let's start at 0 and go to n. And we're going to add those up, but we're going to scale them by t minus tau here. Shouldn't be a huge shock after the last example. If you take a look at the math of how would you get a grade at 62, this thing here, well, we take the grade, say, at 58, and then scale it by g of 4, the difference, which is, okay, how much of that stuff gets over to that point there at 62, because it's 4 away from the point I'm at. and then 57 is 3 away, and then 59 is 3 away, and 60 is 2 away. Each of these values changes where we are on this curve. And so we get a merging or a smoothing of this data set by taking each point here and essentially, I'm waving my hands right now, taking each of these data points and blowing it up across a bunch of different data points nearby. And when we do that, we convolve our two functions here, we get the solution, or we get the new function y of t. So just taking a step back, in most cases, we're going to see some slightly different ones with Laplace transforms, but in most cases for now, when you see a convolution appearing in mathematics, you can think about the math by all means, but I usually think of it as the two ingredients, a signal and something that you're running over the signal, and there's some kind of incrementality to it. So we march across these things and multiply by this function here. Here it's averaging the 7 nearest values, and that ends up giving you a smooth version of what you started with in the signal. In the grades, likewise, it doesn't have to be a straight average. It can be something a little more subtle. Well, the value in the middle is the most important, and the values as you go away get less and less important in some kind of reasonable way, then that gives you something that's going to be a lot smoother looking when you're done. But the math you end up doing for this ends up being the same. Now, last note, Fourier transforms turn out to have really nice ways to compute these sums. For instance, if you think about how you do this in Python, you have a sum here, and you'd have to do a for loop around this for t equals 0 to n to be able to recalculate all the y values. This is a vector of y's. We would need to calculate each one individually. This would be a double loop. That's really, really expensive. It's like 2 massive loops of size n. It turns out with Fourier transforms, we can do it much more quickly, and also get some other insights along the way. So we are going to do these convolutions with Fourier transforms next.